All right, so this section is called graphing polynomial functions, and while it is important to understand, what the graph of a polynomial function looks like, because if you're given a function, it's nice to know kind of the behavior of the function, maybe the end behavior of that function, maybe where you cross the x-axis and the y-axis. But I also realize that we have graphing calculators, we have Desmos. I might have you kind of give a sketch of the graph by hand. I honestly want you to use your graphing calculators. I want you to use Desmos. I want you to use your technology to kind of verify some of this stuff. So in this section, the big thing that I just want to talk about in this section is stuff kind of we already know. I want to talk about how to find X-intercepts, how to find y-intercepts. I want to talk about the multiplicity of zeros and what that kind of tells us. And then maybe just define one thing that's called a turning point, or kind of a fact about a polynomial function that we'll put right now. And that's really about it. And then we'll talk about the intermediate value theorem, and that's all. So again, I want you to have graphing calculators on this section. I want you to use Desmos if you can on the homework. I want you to use those things, but I also want us to be able to describe this function algebraically by finding x-intercepts, y-intercepts, and determining stuff like that. So before we get there, just a couple, I guess this is kind of like a theorem. I'm not going to prove it though for you, so take with this what you will. But this, I'll just call it a theorem. I just forgot how to spell theorem. I have no idea how I forgot that. Graduate school theorem. Sure, that might be wrong, and you can get me for that. So let's let p of x be a polynomial of degree n. Okay, a polynomial of degree n. Then the graph of p of x we know a couple things about the graph. It has at most n real zeros, at most, you guys. So that doesn't mean that it even has to have real zeros. It'll have complex ones, but at most it has n real zeros, and thus at most x-intercepts, because that's where our zeros, right, are where we cross the x-axis. So at most, so for example, we know that the graph of x squared plus 1, right, is a parabola that's shifted up 1. Even though this is a degree 2 polynomial, we just say it has at most 2 intercepts. Clearly this doesn't have any x-intercepts. It doesn't have any real solutions to the zeros. Whereas if this was actually x squared, I'm getting a little crazy over here, getting a little crazy, minus 1, right? That's an example of a polynomial that has 2 real zeros and it's of degree 2. What does that mean to have at most? Could we just have 1 real zero? Yeah, we sure could. What if we had something like x minus 1 quantity squared? We know that this is a parabola shifted to the right one. And we kind of talked about this, that 0 has multiplicity 2. It has an even multiplicity, so it's going to be tangent to the x-axis there. So that's all that this is saying. We can have at most n real zeros. And then the other thing this theorem says is that we have at most n minus 1 turning points. So I'm not going to spend a whole lot of time on that, but what a turning point is, let's just put a little star here. A turning point, okay, is where a relative max or min occurs. Okay, I have a relative max or min there, or another way to say that is where a graph changes from increasing to decreasing, or decreasing to increasing. From decreasing to increasing, or increasing to decreasing. Okay, so that's just kind of the first theorem of this section, and I just wanted to, recognize it. And then what I want to do is I just want to do some examples and kind of show you what I'm going to expect you to be able to do in this section. So, and then we'll look at the graphs of some of these. So let's for these examples, okay, what I would like us to find for these examples, make sure I have what I want here. Okay, so what I want us to find, I want you to determine end behavior. So this is going to be a lot like the last section. Determine end behavior, X-intercepts, y-intercepts. Okay, and what else? I think that's about it. And multiplicities of the zeros. Sound it out, Sarah. Okay, and then the last thing is, and provide a general sketch of the function. And again, I am fine if you use your graphing calculator to provide that general sketch. So, but I want to make sure whatever your general sketch is, right? If you use your calculator or you use an online graphing system like Desmos, whatever you decide your general sketch is, it should match up with what you have done algebraically, finding the end behavior, the X and Y intercepts and stuff like that. Okay, so let's look at kind of a simple function. Let's see. I'm going to be a little bit lazy here and I'm going to use your book. So let's look at the graph of this function here. F of x equals a negative 2x to the fourth, okay, plus 3x cubed. All right, people, so right away, let's look at the end behavior. What do we know about the end behavior of this function, right? I have a fourth. So remember, if I have an even degree, I'm either going to look like this or I'm going to look like this, right? My two ends, I guess, are either both going up or both going down. That's what I know about the end behavior of an even degreed function. And because this leading term or leading coefficient is negative, I know that we're going to select that guy right there. So my end behavior is going to go down like this. I don't know what happens in the middle here, but I do know that I'm going to go down on both sides, okay? There's my end behavior. I want to find my x-intercept and I want to find the multiplicity of my zeros. So the way I find that is I'm going to take my function and I'm going to set it equal to 0. Right, so x-intercepts, remember, are where we cross the x-axis. That means that's where my y or my function values are 0. I see it, I see it, I see it. Okay, there we go. So that's cubed. So I'm going to factor out an x cubed. I would get a negative 2x plus 3. You could take out a negative x cubed also. That might have been nice to do. X cubed equals 0. That tells me that x equals 0, right? And that's one of my zeros. What multiplicity does that have? That has multiplicity 3. So I know because it has an odd multiplicity that it's not going to be tangent to the x-axis. It's actually going to go through it, right? And then where is my other 0? Here, if I solve this, negative 2x plus 3 equals 0, then I get that x equals minus 3 divided by negative 2, 3 halves. Okay, so there are my zeros. What is the multiplicity of that 0? The multiplicity of that 0 is just 1, right? Because it only has one factor, basically. So my multiplicity is just 1. Good. So I'm ready to go. So my end behavior, right? I'm going to kind of, this is kind of all my side work, and then eventually I'll bring this all together. So I have my end behavior, I have my x-intercepts. My y-intercept is pretty easy to find. My y-intercept is going to be f of 0. That's where it crosses the y-axis. So I get 2 times 0 to the fourth plus 3 times 0 cubed. So I know that my y-intercept is going to just be 0, 0. It goes through the origin. Okay, so here's what I know. End behavior is going to look like this. My x-intercepts, right, are going to be 0, 0. Remember, x-intercepts are actual points, and 3 halves 0. My y-intercept in this case, also 0, 0. And then my multiplicity of the zeros, if I look at 0, that has multiplicity 3, and if I look at 3 halves, that has multiplicity 1. So there are all the things that I want you to tell me, okay, about this graph. And then it says provide a general sketch. So this can be kind of tricky to do sometimes. Sometimes if you want to do this without well, not sometimes. If you do want to do this without a graphing calculator, what you can do is you can kind of look at your x-axis and you can kind of break up your x-axis into intervals. Like I would look at between 0 and 3 halves, and I would determine if I'm positive or negative, meaning am I above the x-axis or below the x-axis. given the end behavior of my function, you know, I'm probably going to be negative here. Well, that's not always true. Be a little careful there. But I could actually plug in values. Like I could plug in a -1 into my function here and see what I'm going to get here, right? You're actually going to get a negative. Here you would get positive, and here you would get negative if you plug values on the x-axis into my function. That just tells me I'm below the x-axis if I'm less than 0. This tells me I'm below the x-axis if I'm greater than 3/2. And then, of course, that plus tells me I'm above the x-axis if I'm between 0 and 3/2. The other thing that we need to think about too is this idea of turning points, right? At most, I'm going to have 3 turning points. So let's look at the graph of this and see if this is what we're going to get. So I'm going to go ahead and put in y equals -2x to the 4th, right? Plus 3x cubed. Oh, that's cool. What a cool graph. So look at this graph. This is kind of doing what we would expect it to do, right? I have the end behavior that we had talked about here. Look at my zeros. Where are my zeros? My 0 are at 0, 0, right? And where else do I have a 0? I have that 0 at 3/2 or 1.5, 0. It's also interesting because I have 1 turning point here. Remember, I could have at most 3, but I only have 1 turning point. What else do we know about this function? It's increasing, increasing, increasing until that turning point there, and then it goes to decreasing. When you get to calculus, you are going to find a wonderful way of finding these points, of finding that maximum value right there, and knowing kind of what's going to happen with this. Another thing to think about with this 0, again, you're going to graph these on your calculator using Desmos, but the multiplicity, right, of 0 was 3. So do you see how kind of through that 0 there, I kind of have a cubic looking function almost, and it's not a cubic function, but it kind of behaves like a cubic. That's an interesting point about that 0 because it has multiplicity of a 3. That's why we kind of get that cubic looking function here. Here at this 0 at 3.5, remember that was multiplicity 1. And if you zoomed in on this, which I have the power to do that. If we zoomed in on this 0 and we got really, really close, do you see at this 0 it would almost look like a line? And again, that had multiplicity 1, so that makes sense. Here I had multiplicity 3, so I know I'm going to kind of look like a cubic through this sky right here. If you're really sad about not graphing these by hand, of course you are welcome to graph them by hand. But I just know I don't graph these by hand anymore. I use my calculator, I use Desmos to do it. But the algebra is still very interesting to talk about, and how the algebra agrees with what we had, or excuse me, the graph agrees with what our algebra found us. Okay, so let's do another example. I want to do the same stuff. I want to find, oh yeah, I know. I want to do the same stuff. So I want to find, you know what I'm saying. Let's do part B of the same example. I want to find X-intercepts, y-intercept, all of that good stuff. Okay, so let's look at, I'm going to grab one from your book here. Let's look at the function f of x equals, let's get x to the 5th minus 4x cubed. Okay, and I'm going to just start over here putting my answers. So my end behavior on this function, this is odd, so I'm either going to do this, right, for my end behavior, or I'm going to do this for my end behavior. Remember, this one's if I have a positive coefficient, this one's if I have a negative leading coefficient. I have a positive coefficient. So my end behavior is basically going to kind of look like x cubed, except because it's to the 5th, it might do some funky stuff in the middle there. Funky stuff, total math term. X-intercept, where do I cross the x-axis? X-intercepts occur where I cross the x-axis, which is also the same as y being 0. I'm going to take out that x cubed. I'd be left with x squared minus 4 equals 0. So what are my x? Well, my zeros here then are 3. And then this guy is, right, x minus 2 times x plus 2 equals 0. So I have x equals 2 and negative 2. So my x-intercepts, I'm going to go through 0, 0. I'm going to go through 2, 0. So by you, I didn't put the negative 2 first. It's kind of bothering me. Negative 2, 0. These are going to be my x-intercepts, okay? And then we'll talk about our zeros here in a minute. Y-intercept. I'm going to put in, this one's, sorry, a little bit boring, because if we put in 0 again, we get 0 for our y-intercept. Oh no, that's a 0. So I know I go through the origin. If our x-intercept's the origin, then we're going to have a y-intercept that's 0, 0 also. And then the multiplicity of the zeros, if we look at 0 here, 0 has multiplicity 3, 2 has multiplicity 1, and negative 2 has multiplicity 1. So I would, if you think about graphing this, I would assume at 0, 0, because it has multiplicity 3, it's going to do something like that. At 2, right, it's just 1. And then at negative 2, it's also 1. So I'm going to guess that my graph is going to do something. Oh, no, I have that wrong, don't I? Because my end behavior wouldn't work for that one. So let's look at this again. This is why we use Desmos. Well, we don't have to use Desmos to do it, but I know I have this, I know I have this, I know I go through here, right? I know my end behavior it's going to probably do something like that, okay? Something like that, where I could plug in, 1 and negative 1 and figure out kind of what the graph is going to look like, but I am going to use my Desmos instead and do that with Desmos. So let's look at what Desmos tells us about this, or what we could get if we used our calculators. So x to the 5th, and then what did I have? Minus 4x cubed. Wow, that x is a little crazy. Nope. Yeah, oh wow, this is way different than what I had guessed. And if I had put in some values here, oh, that one is so cool. Yeah, and that makes more sense if you look at the zeros there. So I was a little off on the zeros there. We come up, right? We have a turning point right here. Remember, how many turning points do we have here? We have 2. We can have a maximum of 2, right? We can have maximum of 4, excuse me, n minus 1 turning points. And again, if you look at these zeros, look at the behavior of this function. I have kind of a cubic behavior at 0. Granted, it's like a negative cube, but it's still a cubic behavior at these zeros. I kind of have a line at negative 2, and I have another line at 2. Sorry about graphing that wrong. This is why we use graphing calculators and Desmos. So I hope that makes sense. Look at what we have. We're increasing. Then at the turning point, we go decreasing. We stay decreasing until this other turning point, and then we go increasing again. It's going to be great when you get to calculus. You'll find that these points right here are what we call critical points, and we see that our derivative at those points are 0, which is pretty fun. You'll like that. I hope that makes sense. These are pretty, I know I'm being a little bit lax on these, but I want you to use, so again, why was I incorrect right here with this graph? See, now that's bothering me. I should have, because this guy right here is degree 3, I should have some sort of some sort of like cubic function that goes through there. I need to just leave it alone. Leave it alone, Sarah. There's my cubic function. I didn't quite go down enough and grab it. All right, so let's look at last thing I want to talk about. No, that's not, I did 2 examples. I'm sure you will feel comfortable finding x-intercepts, finding y-intercepts. That's your basic setting stuff equal to 0. But before we go, what I want to talk about is the last part of this section, and that is what we call the intermediate value theorem. So it's actually a pretty interesting theorem, and this is a theorem that you'll use. I know I keep talking about calculus, but it's the best. So intermediate value theorem is something that is actually pretty important. So let's let p of x be a polynomial function with real coefficients. That's pretty obvious to you probably, but we can talk about polynomials with non-real coefficients. With real coefficients. And suppose for some a and some b, and let's say that they're not equal, okay, p of a and p of b are of opposite signs. So all that says are, of opposite signs. All that says is that one of them Okay, so if I take P of A, I get a Y value, maybe that's positive. If I take P of B, I get a Y value, that's negative. That's all that's saying, that I have one above the x-axis and one below the x-axis, that's all. Okay, then if that's true, this should be pretty obvious. Think about if I have a polynomial where some A gives me a positive or some B gives me a negative, what do I know about this function? Because it's a polynomial and polynomials are continuous everywhere, I know that I must have at least one zero. I must have at least one zero. Then the function, okay, has at least one. It could have more than one. Real zero. And where must those real zeros occur? Well, if this is my A and this is my B, right, that real zero must occur between A and B. Between A and B. Okay, so I want that between A and B. Now, if A and B, if P of A and P of B have the same sign, meaning they're both positive or both negative, this intermediate value theorem doesn't tell us anything about a zero. Okay, so that's all it is. So let's do a quick example. This is going to be pretty easy. Use the intermediate value theorem, or the IVT if you're cool. That makes you cool. To determine, if possible, okay, whether f of x, whether, oh wow. Is that how you spell weather? That looked really weird. F of x has at least one. I am sorry, I don't know why I can't spell today. Has at least one real zero between A and B, the A and B given. We'll do a couple of these. And then we'll be done. This is going to be like a record for me. It's going to be a short lecture. So if I have f of x maybe equals x cubed plus x squared minus 6x, and I give you that a is -4 and b is -2, okay? Again, what does this intermediate value theorem say? If I evaluate my polynomial at A and I evaluate my polynomial at B and they're opposite signs, then I'm guaranteed that there is a zero between -4 and -2. So this is going to be a little small, sorry. So f of -4, -4 cubed is a -64. -4 squared is a +16. -4 times -6 is a +24, right? So let's see, -64 plus 24 is a -40 plus 16. So this guy is a -24, I believe. You should really, really check me on that, because arithmetic is difficult for me sometimes. All right, so I have that f of -4 is negative. Let's find f of -2, and I'm just going to kind of figure out what this is. So f of -2, right? I'm going to do a little bit of work right here. We give me -8. -2 squared is a +4. -2 times -6 is a +12. Okay, so I have a -8 plus 4 is a -4 plus 12 is a +8. So look at what I know. I know that that I'm below the x-axis at -4, but I'm above the x-axis at -2. So what must I know that I must have gone through the x-axis, right? So the intermediate value theorem tells me that yes, there is one real zero, at least one real zero between -4 and -2. You don't know how many, right? We would actually have to find those zeros to figure that out. You don't know how many there are, but we know that there is at least one, okay? Let's look at one more, and then we'll call this good. This is amazing, getting through this so fast. Oh, yeah. Okay, so part B, wow. No idea what just happened there. That was pretty cool, though. All right, part B. So let's look at another one. Let's say f of x. Let's try 1/3 x to the 4th minus x cubed. And we're going to look at a being 1 and b being 2. Okay, so f of 1, that would give me 1/3 minus 1, which is a negative 2/3, right? And f of 2 then, 2 to the 4th is 16. 16/3 minus 2 cubed is 8. So if I look at this, I would have 16/3 minus 24/3, right? Which gives me a negative 8/3. So does the intermediate value theorem guarantee that I have a 0 between 1 and 2 in this graph? No. Now, does that mean there isn't a 0 there? Not necessarily. There could be a 0 there. I don't know that. There could be. But the intermediate value theorem does not guarantee that there is one, okay? Because all we know is that whatever we're doing here, we should be at 1 and 2, sorry, 1 and 2. All I know is that these 2 points lie on the graph. I don't know, it could come up and do something like this, right? And I get a 0, but I don't have anything that tells me that for sure that 0 is there. All right, you guys, that's it. 25 minutes. So again, I want you to do a quick sketch of the graphs, but you can use your calculator to do that. But I want you to make sure that your graph that you find on your calculator or in Desmos matches up with what you have found, your x-intercepts, your y-intercepts, your multiplicity, all of that good stuff.